Our final speaker for this session will be Dr. Jeffrey Siwo. Dr. Jeffrey Siwo also wears many hats. He is a research assistant professor in the Department of Learning Health Sciences at the University of Michigan Medical School, as well as the Michigan Center for Global Health Equity. His work spans a wide range, very wide range of fields, from systems biology to AI, drug discovery. And in the process, he's co-founded two companies, biotech companies, very impressive. So Dr. Siwo is going to be talking about exploiting large language models and improving the causal reasoning of them. Thank you.
Yeah, thank you so much, Josh, organizing this amazing meeting. Excellent talk, Wes. And yeah, I actually did my PhD in Michael Fadig's lab. We still continue to collaborate, so I really enjoyed your talk. And your talk kind of bridges my past. I still collaborate with Michael Fadig. I have some work on synthetic data generation using one of the methods you showed there. So feel very much at home. I'm sure there's many people in this room you intersect with in different levels. I also want to mention that because I've met several amazing data scientists in this meeting at the University of Michigan. We have a new program funded by the Eric and Wendy Smith Foundation, focused on building AI in science fellows, especially in Africa. So I encourage you to take a look at that new program. And being in the medical school, I'm required to make my disclosures. So as mentioned, I'm confounded and I've been involved in some clinical stage biotech companies now, and also advise some companies, including Google Research. And my research on large language models spans a wide range of areas. I have worked for probably more than 5 years. So before GPT, I worked on the historical transformer models, like the BART model that preceded GPT. Before the public launch of GPT, I also leveraged the GPT architecture in developing AI models to design small molecules. So you can use the same architecture. You can train it on text, but you can also train it on different kinds of data, like small molecule or chemical structures. And we've done that work also with the DNA and RNA and proteins, as well as now at Michigan, looking at thousands of diseases, trying to understand how can we leverage these LLMs to help us understand the relationships between all the diseases we know, because we know that all diseases are related in a way, and understanding these relationships can help us to diagnose diseases better, as well as develop more effective therapeutics. I actually think that one of the most important strengths of LLMs is the ability to help in encoding information and not necessarily in question answering. So encoding information, meaning that, to process anything on a computer, it has to be in a digital form, but it also has to be in a form that is computable. So you can assume that everything that is computable should be in numbers, right? And historically, science was about numbers, right? When you talked about science, you had to show numbers, right? You have to count and do statistics, right? And so even when you are faced with problems like imaging or text, you're still forced to try to count before you can process it on a computer. LLMs allow you to encode that information and then use the encoded information in different ways, of which question answering is just one of them. So I'm very interested in how to build on today's LLMs, especially enable them to reason about the world. Because one of the major limitations of LLMs is that, large language models predominantly, they work by trying to predict the next word, right? So this is the foundation of LLMs. This has been, in fact, the foundation of many natural language processing approaches, including sort of the ancestral versions of GPT. And so I think for this meeting, everybody is convinced that LLMs are going to have a huge impact on health. So I don't need to convince you about that. But maybe we can reflect on the challenges that LLMs pose. So first of all, one of my biggest fears about LLMs, right, is that that even though we use LLMs across organizations, we don't have full visibility of these LLMs, right? We don't have full visibility, we don't have full control. So if you're a large healthcare organization like Michigan, and you, let's say, use one of these models, right, and build on it, it's developed by a company, right? What happens if the company goes away, right? Of course, everybody knows that, oh, we've been relying on Google. Google has never gone away, right? But we have to think of these questions, especially in this rapidly evolving field in which we have the first comer. So OpenAI, first comer. And historically, we've seen what has happened to first comers like Netscape, right? So LLMs can also be costly to operate. I think also one of the major problems with LLMs is that actually there's no standard way for benchmarking LLMs. So how do you actually know that your LLM is performing very well, right? So every company, when they make their LLMs models, they publish them, they do their own benchmarking, right? So judge and jury, we know what happens, right? Nobody wants to say that theirs is the worst, right? So we see that everybody's LLMs tends to be the best when they publish it on a given problem. And then, of course, we all know that because LLMs are not based on any kind of reasoning, that LLMs can confabulate answers, which you say hallucination. But of course, we are giving the LLMs too much credit, right? They're not hallucinating, right? Because to hallucinate means you actually have some kind of thought. They do not, so they're not hallucinating. They're just making errors. And so we need to think about the fundamental constraints of LLMs. And I think this probably goes across the board for all AI approaches, right? That you cannot solve everything by data. So you need to know, what can I actually solve by data? And even though LLMs are very complex, in many ways they're still probabilistic. And they're detached from the realities of the natural world, right? Because they just try to predict the next one. They don't have to do the hard work of, even to do math. LLMs don't have to do the math, right? They just try to predict what comes next. And we know that LLMs are actually out of the box, not very good at math, right? And that's a hard problem for them to solve, although there are innovative ways of doing that. So there are limitations of the way we evaluate LLMs today. We know that predominantly LLMs are evaluated based on standardized exam questions, right? So like USLME for medical exams, right? And I think there's a big problem with that because these are standardized tests. So the fact that the LLM gives you good answers does not necessarily project on how it will perform in the future. There's no consideration of real patient data in the benchmarking of these LLMs. Often it's based on the standardized questions, but then projected into applications that involve real patient data. So they can get good grades, even though they may not be really good. So I believe that LLM should be enabled to use reasoning before providing answers. And we know, this is one of the exciting frontiers of LLMs and AI, is that how can we make AI systems that are robust, that integrate knowledge, not just data, so that we can have robust systems? Because data is about the past, right? So you cannot purely rely on data to predict the future. You need to move out of the past to be able to predict the future. And for things like physics, we know that there's standard natural laws that that the natural world operates in, right? And so we know for generative AI, you can create fake videos, but those fake videos, they don't have to be natural laws, right? And so that's one way that you can know that this image is fake or not if you put it to the test of those natural laws. And so we're developing a new approach that we call chain of cause reasoning. Chain of cause reasoning is inspired by Daniel Kahneman's book, Thinking Fast, Thinking Slow. The late Daniel Kahneman wrote this wonderful book thinking about, that as humans, every day we experience challenges that requires us to react instinctively. And even in a way, talking is almost instinctive. You don't have to think. But if I give you a tough problem, you're not just going to try to like cook up the answer step by step, right? Like LLMs do. You're actually going to take a pause. Like if I give you a math problem, take a pause, think about the problem, and then try to solve that problem. So this is what we need LLMs to be able to do, so that they can be more robust, so that they can also explain the way they come to their solutions. And this is sort of system 2 thinking, meaning that a slow, conscious process, perhaps even with some self-reflection or introspection, because that helps you to also assess your answer and walk back. And sometimes, as humans, you give an answer, but actually if you begin to think about it backwards, you find that it doesn't make sense. And I think we need to enable LLMs to do that. So this approach that I call chain of cause reasoning is distinct from another approach called chain of thought. And chain of thought is basically a way to enable LLMs to explain how they come to answers step by step. So the recent GPT Omni that was launched has some chain of thought already integrated into it. By several experiments, what you've realized is that actually LLMs are good at cheating, right? So even when the LLM tells you that this is the step-by-step explanation of how I came to the answer, many times you'll find that if you take those step-by-step, you don't arrive at that answer. So it's not using that step-by-step, even if it makes sense. And in some cases, it gives you the right answer, but the step-by-step would take you to the wrong answer. So basically, it's not using the step-by-step process. And this is, I think, is a major problem of LLMs, because for many technical problems where I've tried to apply LLMs, and I think a lot about DNA and RNA. So LLMs can do some basic manipulation of RNA and DNA sequences, and normally you find that the answer looks kind of correct, but if you begin scrutinizing very closely, you find there's a hidden error somewhere. And so I think we need to be worried about that when it comes to LLMs. So the way chain of cause reasoning works is that, first of all, we try to ground these LLMs, and we ground them by giving them some causal relationships about the real world, or about the problem that we are interested in. And there can be many ways of getting those causal relationships. Then after that, the LLM is forced to use the causal relations in the real world. So constrained to think about those causal relations of how things work to come up with an answer. So there are different ways of getting causal relations. So you can have causal graphs that are curated manually by experts sitting down and figuring out, let's say for malaria, what are the things that affect like breeding sites of malaria? How does that relate to transmissions? So you can draw these complex causal graphs, and then these causal graphs can then be ingested into LLMs to help them reason about malaria transmission. You can have expert curated knowledge graphs. So knowledge graphs are kind of like causal graphs, with the only difference that they're more precise in the way you specify knowledge. So for instance, in a knowledge graph, trying to show relationship between diseases and drugs and genes, you can see that the relationship between a disease and a drug is that a drug treats a disease. So this can be constraints that can be fed into LLMs. And then you can also use causal discovery from observational data using AI. And we have a project funded by the Gates Foundation trying to use health and demographic surveys to figure out how different health interventions have a causal effect on specific outcomes. And then, of course, you can combine all of those. And in fact, you can also use LLMs to generate initial causal graphs that are then assessed before an LLM is allowed to use them to generate answers. And I'll give a quick example. So giving ChatGPT a question from USLME about an HIV expectant like mother who gave birth, and are trying to figure out which test is the best to perform on the baby in order to determine whether they're HIV positive or not. So the way chain of cause reasoning would work is that actually chain of cause reasoning would first come up with a causal relationship graph of all the the factors that are in that question. So HIV, the mother, the baby, like to figure out how all of these are causally related. And then out of the box, you can ask, even though ChatGPT didn't use to draw, you can take it into drawing. So this is the interesting thing with these systems. You can take it by telling it to use ASCII 2, which is, just the alphanumeric character. So you can make it to draw things, even though it doesn't typically like draw. So you can ask it to come up with a causal graph. You can access that causal graph. Then you can use that causal graph now as an additional input to ChatGPT to come up with an answer. And if you do this, you find that now ChatGPT is giving you an answer, and it reasons using the causal graph that you had given it before. But what I'm excited by is that we notice that when you ask ChatGPT to generate causal graphs, sometimes it gives you a graph where the causal relationship makes sense, but actually in the drawing, it can get some arrows wrong. So maybe it will point that this factor causes this, while it's the reverse. And ChatGPT can also write code. You can actually ask it to write R code to draw for you that diagram. And also with that, realize that, most of the diagram looks fine, but there's just a few nodes that normally things are misplaced. So you have to manually, again, assess. So the other thing we're doing is actually to take ChatGPT and then try to see if you can generate standardized knowledge structures. So there are standard ways of presenting knowledge. So one is called, you can use RDF, which is the resource description framework, which is a way for representing knowledge in knowledge graphs. And so in this knowledge graph, you see that, for instance, like mother has condition HIV. So you have mother, which is the subject, and has condition shows the relationship between like the mother and HIV, which is has condition. So the interesting thing about having this kind of graph is that they're very good knowledge reasoners that don't use, they don't use LLMs, they use logic, right? So you can apply logic to come up with answers that are logically bounded. So combining the sort of old AI with this kind of like new AI. So you can use that generate knowledge graph to now enhance the answer. And you can do that, for different diseases. So we are still trying out to see to benchmark. So we have tried also like with malaria. I won't go into details because of time. But the main message to show that basically you can also use the LLMs to accelerate the way we construct knowledge graphs. Because we know that once you have knowledge graph, like Google has a knowledge graph between different like objects in the world that helps to enhance its search engine. So once we have this knowledge graph, then we can make even better decisions that are logically grounded and that we can explain, and that could also enhance the performance of LLMs. I was going to share an example whereby you can use this kind of knowledge graph to test different scenarios of the impact of an intervention. So, for instance, like a knowledge graph about like both malaria transmission and interventions like vaccines and emergence of drug resistance, and then you can try to see or to explore different scenarios and see whether, like, given that knowledge graph, can ChatGPT or GPT give you a better answers. So in summary, the advantage of chain of cause reasoning is that you have some causal reasoning. And I think this is important because unlike question answering is kind of bounded by the questions you give the LLM, but because knowledge can be generalizable, right? If I give you even just one sentence of knowledge, like tell you the color of like oranges, right? That's just a piece of knowledge. I haven't given you like a million oranges, right? I've told you what the orange is, and you can deduce from the description of the orange to tell what oranges look like. You don't need all the data to know what oranges are, right? And so this can enable LLMs to do that. It can enable LLMs to be explainable and hopefully also avoid confabulating things, because now you ground it on real world knowledge. And I think importantly, you can now integrate LLMs, which are highly probabilistic, with the logical reasoners, which are well developed, right? So like in mathematics, they use theorem provers, right? And theorem provers, they do like logic, right? So you can apply logic to the output coming from GPT to see if it is bounded by what is logically reasonable. So of course, the limitations. So this is a method we're still developing. It requires like a causal framework.